Good morning. Now I want to discuss ideal solution and non-ideal solution. The first, ideal solution. What is the meaning of ideal solutions? In case of gaseous system, we have seen the ideal gas law, PV equal to nRT law, and in gases, practically there is no ideal gas. But in case of ideal solution, we have the ideal solutions. So what is called ideal solution? As per the definition of the ideal solution, we can say that the solution which follow the Raoult's law in all conditions. So first thing, follow Raoult's law in all conditions. That is called ideal solution. Not only that, when you make the ideal solution, delta H mixing, that must be 0. What is the meaning of delta H mixing? The delta H mixing means enthalpy of mixing. Normally what is happening, if you make the two liquids, two component during the making of the solution, sometimes it has happened that the solution becomes exothermic, that means temperature released. Sometimes it is endothermic. But during ideal solutions, there should not be any heat change during the mixing of the two component. Number 3, delta V of the mixing. Delta V of the mixing means during mixing, volumes should not change. Suppose if you take 1 liter of component A, 1 liter of component B, and after mixing, it must be practically 2 liters. It should not be the more than 2, it should not be the less than 2. In reality, we are getting different volume. So we will discuss in details about that. But in ideal solution, the volume must be constant after mixing and before mixing, and during mixing should not be any change of temperature. And practically, if you think that what is the cause of the ideal solutions, practically molecular interactions plays important role. So actually it has happened that solute molecule interact each other, solvent molecule interact each other. In case of ideal solution, the interaction between the solute and solvent must be equal to the interaction exhibited by the solute-solute as well as solvent-solvent. Now question is there any example? Yes, we have different example of Raoult's ideal solution. The best example you can take is mixture of benzene and toluene. Or we can take another example, cyclohexane, cycloheptane. So these are the different examples of ideal solutions. Now, in case of ideal solutions, if you think carefully, total vapor pressure, graph we can explain this way. If you plot vapor pressure axis, this is another axis I am taking, mole fraction axis. So, as per the Raoult's law, I am taking first pure A component, and where I am taking xi equal to 1. I have not added B, so then x b equal to or xi b equal to 0. And the vapor pressure exhibit by the component A in the pure state, that is P naught. If you add the component B, obviously vapor pressure decreases because mole fraction of component A decreases. That can be explained by this type of graph. So this situation is coming xa 0, xi b coming 1. And in this situation, the B component behave like a pure B component, and the pressure exhibited by the B component I am thinking that is PV naught. So initially when the B was 0, the vapor pressure was 0. If you gradually add the B, the vapor pressure of the B component increases and you will get a situation like that. So this is the graph for the PV naught, and here PA, this is PV equal to PV naught xi b, PA equal to PA naught xi. So now total vapor pressure, earlier we have seen when we are making the Raoult's law in case of volatile solute, we just made one expression, total vapor pressure, P total. So P total can be expressed from this type of line, and it's a linear line. We can write like this. So that graph the slope of the graph that give you PA naught minus PB naught, and we are getting that this is the graph for the ideal solutions. Next we will think the non-ideal solutions. For non-ideal solutions, we can say that they don't follow the Raoult's law at any conditions. So non-ideal solutions. Simply we can say that they do not follow the Raoult's law, don't follow the Raoult's law. Raoult's law deviated in non-ideal solution. And if you study that, we got that there are two different type of deviation is found. One is positive deviation of the Raoult's law, and another deviation we are getting, that is the negative deviation of Raoult's law. Now let us discuss about the positive deviation, why it is happening. In case of positive deviation of Raoult's law, we found that the delta is mixing, enthalpy of mixing, that is positive. That means after mixing two components, the volume, the heat, that is not volume, heat decreases. Second, another important observation is found, delta V mixing, that is also positive. What it indicate? That indicate after mixing, volume increases. Now let us discuss the mechanism of the formation of the positive deviation of Raoult's law. Actually, it is happened that when you add the component, suppose A and B, after adding the component, it is found that the interaction between the A and B component, that is less compared to A or BB. That means if interaction is less, that means the molecule become expanded and volume increases. So that is the main cause of the positive deviations of the Raoult's law. And there are varieties of example we are getting which shows the positive deviation of the Raoult's law. The best example, if we dissolve ethyl alcohol with water, methyl alcohol water. So many examples. This is just simple one example I am giving. One example is like that. Similarly, you can dissolve, you can mixing cyclohexane plus ethyl alcohol. So that is also give the example of the positive deviation of Raoult's law. And if you make a graph which represent the mole fraction and vapor pressure compared to ideal one, earlier we learned the ideal solutions, and if you compare the graph based on the ideal solutions, you see this is earlier we learned this type of graph. It was PB naught, xb equal to 1, x equal to 0. This is x equal to 0, 1, P naught. And this was the ideal graph. But now for positive deviation, what we are getting, in both the cases, the more vapor is formed, it should look like this. So the graph is like that. This is P total is follow this type of graph we compared to the ideal one. Similarly, another deviations, that is a non-ideal deviation, non-ideal solution. Negative deviations, that is also non-ideal solutions, negative deviation of Raoult's law. So if you think the negative deviations, so here delta is mixing, that become negative, and delta V mixing, that is also negative. What it suggests, that means after mixing, heat will produce, that is exothermic reaction, and volume must decreases. So why it is happening? Now after mixing A and B component, the internal attraction force increases compared to individual A or BB. So then solvent-solute interaction when more compared to solute-solute or solvent-solvent interaction. So then we get the negative deviation of Raoult's law. So after mixing, volume decreases. There are so many examples of such type of solution. One of the best examples, if you take the ethyl, that is chloroform, CHCl3, and if you mix with CH3CO, CH3, what is happening here? Here it is happening like that. This chloroform can form hydrogen bond with acetone, and due to this formation of hydrogen bond, the volume decreases. This is the reason. Not only this, so other example we can get, like HCl if you dissolve in water, we are getting the similar type of situations. So this is the two type of solutions. And here if you again make a graphical presentation of the negative deviation Raoult's law, this case if you see the graph, it will look like this. With respect to the ideal solutions, I am writing this the ideal solutions, PV naught so this case the nature of the graph is just like that. PA, PV and total vapor pressure also, that is expressed this type of graphs. So now here one related topics is there after the ideal and non-ideal solution, a new topics that is called azeotrope or azeotropic mixture. Azeotrope or azeotropic mixture. Azeotropes or azeotropic mixture. Actually, azeotrope means it is a mixture of more than one component, more than maybe two components. They behave like a pure liquid during distillations. That means their boiling point remain constant and their composition also remain constant during distillations. So azeotrope is a solution whose boiling point is fixed and during distillation their component, their different component, they remain behave like a solutions, and that type of mixture is called azeotropic mixture. When you study, there is some correlation between the positive deviation and negative deviation and azeotropic mixture. Actually, when you study azeotrope, there are two different types of azeotrope we are getting. One is called lower boiling point azeotrope. And another is higher boiling point azeotrope. What is the meaning of lower boiling point azeotrope? Actually, the solutions or the mixtures which form positive deviation of Raoult's law, they exhibit the lower boiling point azeotrope. Again I repeat it, the component which form or the solution which exhibits positive deviation of Raoult's law, they exhibit lower boiling point azeotrope. Because the reason is very clear, there is some relation between the boiling point and vapor pressure. What is the relation? Now when the vapor pressure equal to the atmospheric pressure, then liquid start boiling, and that is called boiling point. So in case of positive deviation, we have seen the vapor pressure is more compared to the ideal situations. That means liquid start boiling before the boiling point of the actual component. That means, for example, if you take the 95% solution of ethyl alcohol, so they form the azeotrope. And you know that ethyl alcohol means C2H5OH plus H2O. And if you see, if you try to distill this mixture, 95% mixture, the temperature at which they start distillations, that will lower the boiling point of the ethyl alcohol. You know that boiling point of the water, that is 100 degrees centigrade, and boiling point of the ethyl alcohol, I think 72.5 degrees centigrade, 4 or 5 degrees centigrade, and this is 100 degrees centigrade. But if you make a azeotropic mixture, so then this entire liquid that is distilled 72.1 degrees centigrade, that is lower than the actual boiling point of the component, and because of that they form the positive deviation of Raoult's law. Similarly, another type of azeotropic mixtures we are getting, that is a higher boiling point azeotrope. Normally, those solutions which form the negative deviation of Raoult's law, they also form the higher boiling point azeotrope because their vapor pressure is less. So if you take 20% solution of HCl, so they form the higher boiling point azeotrope. That means their boiling point will be more compared to the boiling point of the individual component. Okay, so these are the azeotropic mixture. So what we learned the ideal solution, non-ideal solution, as well as azeotropic mixture.